In this lesson, you'll be learning about conditional probability and tree diagrams. As you can see by the definition for conditional probability, it's the probability that the first event is dependent on the probability of the second event, and is usually highlighted by the phrase given that. Using the notation, on the next line, you'll see it's PA with the vertical line B. That vertical line can be read as given that, or just given. So you might read that as PA given B. As you can see in the orange box, in general, for two events A and B, the probability of A occurring given that B has occurred can be found using this formula. The probability of A given B is equal to the probability of A and B divided by the probability of B. This you may see, even in your formula booklet, referred to as the multiplication rule. Or general multiplication rule. And this is what we use in tree diagrams. Right? The multiplication rule can be derived from the conditional probability rule just simply by cross multiplying, and you get PA and B is equal to the probability of A given B multiplied by the probability of B. And again, that's the general multiplication rule. Okay, for all cases. So for this problem, there's a class of 30 students, 12 like to play golf, 17 play hockey, 3 play neither. We're asked to find the probability of the student chosen at random likes to play golf. Again, to start this problem, it's probably useful to use a Venn diagram. And we know that there will be overlapping circles, because again, if you look at the total, right, we have 12 and 17, 29, and 3, 32. So we have more than the total number of students in the class in the sample space, so that we know some must have been counted twice. Obviously, if the total is 32 and we know there's 30 in the class, 2 were counted twice, those go in the middle there. Then, if we call this circle golf and this circle hockey, that means that 10 play only golf and 15 play only hockey. And we know about the 3 that play neither. If you add up all of these values now, 10 plus 2, 12, plus 15, 27, plus 3 makes 30. That accounts for the entire sample space. Part A asks, the probability that the student chosen at random likes to play golf. All right. So that's simply the probability of liking golf. And that's straight from the given. That's 12 out of the 30 students, which should simplify to 2 over 5. In B, the probability that a student chosen at random likes to play golf and hockey. Again, using our notation, golf and hockey is equal to, again, we can simply use our Venn diagram in this case, so it's 2 out of the 30, which can again be reduced to 1 over 15. And then last, in part C, and this is very often too how the IB questions are structured. You'll quite often be able to use information or answers that you've obtained in earlier parts of the question in the last part. The question in C says the probability that a student chosen at random likes to play hockey, given that the student likes to play golf. And again, whenever you see the wording given or is known, that part comes after the vertical line in the conditional notation. So this we'll use the notation, we'll write it this way, the probability of hockey given golf. Okay? In this case, the wording is very obvious. The word given is used. Sometimes it may not say given, it may say something like is known, it is known. All right? Anyway, using the rest of the formula, put the put the letters in their appropriate spots. So it looks like this, probability of H and G over the probability of G. And now we can calculate that. We know the probabilities. Those are, again, what we just calculated above. 1 out of 15 and 2 out of 5. The calculation for that, obviously, 1 over 15 times 5 over 2. And we get an answer of 1 over 6. 5 and 15 cancel to leave a 3. All right, the next problem. In a class of 40, 34 like bananas, 22 like pineapples, 2 dislike both fruits. This time we're asked to draw the Venn diagram, but again it makes sense to draw a diagram for this type of problem. And again, if you add it all up, the 34, the 22, and the 2 add up to much more than the 40. So we know that they are intersecting circles. The sample space again is 40. We know that 2 dislike both, so those will be outside of the 2 circles. And one of the circles is for pineapples, one of them is for bananas. All right. Now, of what's remaining, besides the 2 that dislike both, there must be 38. But if you add up the 34 who like bananas and the 22 who like pineapples, you come up with 56. So the difference between 56 and 38 are the ones who like both, which should be 18. As soon as you know that 18 like both, you know that there's 4 who like just pineapple and 16 that like just bananas. Now we can answer the questions. Again, just as a double check, add up the numbers in the box. 4 plus 18, 22, plus 16, 38, plus the 2 make 40. So we've accounted for all of them. Part B, find the probability that a student chosen at random likes both fruits. So we want, this is, liking both fruits is pineapples and bananas. And again, taking off the drawing, it's 18 out of 40, which can be reduced to 9 over 20. Reducing is not necessarily required. C, likes at least one fruit. At least one fruit is either pineapples or bananas or both. So again, using our notation, it will be this. And from the drawing, again, we know that everything within the 2 circles has to add up to 38. So that's 38 out of 40, and that reduces to 19 over 20. In part D, the question asks, likes bananas given that he or she likes pineapples. So using the notation, it will be bananas given pineapple. And again, inserting the variables in the proper location, this will give us the probability of bananas and pineapple over the probability of pineapple. Again, using the probabilities we've already calculated. Bananas and pineapples. Oh, it's important to note here, bananas and pineapples is the same as pineapples and bananas, like we calculated in B. When it's intersection, the order of the 2 letters doesn't matter. Okay. And on the bottom, probability of pineapple, as we can see from our Venn diagram, is 11 over 20. And if you remember from the work that we did with calculus, we know that this kind of fraction should reduce to 9 over 11 if the denominators are the same. And then in the last part, E, dislikes pineapples given that he or she likes bananas. Again, using the notation, dislikes will be not pineapples given bananas. And again, using the formula, that'll be the probability of not pineapples and bananas over the probability of bananas. And again, putting in the probabilities that we know. For the value in the numerator, we can read that out of the table. So it's not pineapple and bananas. That has to be the group that is 16. So 16 out of 40 over, and the probability of liking bananas is the 34 out of 40. And again, we should know that that fraction reduces to 16 over 34, and in lowest terms would be 8 over 17. On to probability tree diagrams. Tree diagrams are quite useful in a number of different situations, but it's usually with repeated trials, and where, like it says in the definition here, the list or a grid is impractical. And again, you'll start to get a feel for when trees are appropriate. Definitely required when, in cases of replacement or not replacement, they're definitely required in the not replaced case, okay, as the probabilities change from trial to trial. All right, we'll answer this question. A bag of marbles has 4 blue, 2 green, 1 yellow, all right, in it. A marble is taken from the bag one at a time. What is the probability of getting 2 blue marbles if the marbles are replaced? So in that case, the probability of 2 blue can be calculated. This is independent, basically, right? So it's probability of blue times the probability of blue, and those probabilities are the same from trial to trial. So that would be 4/7 times 4/7, which would give us a probability of 16 over 49. Without replacement, as in part B, go to a clean page here. To answer that question, really what we're doing is we're doing the probability of blue and blue. All right, and using the multiplication rule for the multiplication rule for events, the formula will look like this: the probability of blue times the probability of blue given blue. So what we're going to do is we're going to draw the tree diagram for this. Okay. So on the first draw, all the things that could happen are we could choose a blue, a green, or a yellow, and the probabilities of those are 4 over 7, 2 over 7, and 1 over 7. This is called a weighted tree diagram, where you have the probabilities written right on the branches. And we actually only need to expand this tree diagram only for the blue, because we're interested in seeing what the probability of blue and then blue again would be. So on the second draw, again, you could choose either a blue, a green, or a yellow. But here you have to realize that if the marble's not being replaced, the probability of choosing a blue the second time, there's going to be 1 fewer blue marble in the bag and 1 fewer marble overall. And so that would result in a probability of 3 over 6. For the green marbles, a green marble was not selected the first time, so both greens are still in, but there is 1 less marble in the bag, and that makes that probability 2/6. And for the yellow, again, a yellow was not selected, so that yellow marble is still in the bag, and again, out of the total of 6. One thing that is, again, important to note here is, within the branches of a tree diagram, all the probabilities must add up to 1. So for example, you'll notice here, 4/7 plus 2/7 plus 1/7, all of those probabilities equal 1. Likewise, the 3/6 plus 2/6 plus 1/6, all of those probabilities equal 1. So that must always happen. Within a branch of a tree diagram, the probabilities must add up to 1. So anyway, we're going to use the formula that we wrote here at the top. And we'll start with the probability of blue to start with. That was the 4/7, all right? And the probability of blue, given that blue happened, is the second blue probability, which is the 3/6. So we multiply by 3/6. Do the multiplication, we get 12 over 42, which could be reduced to 2/7. All right. The next example. A box contains shoes of different colors. The colors are 4 white, 2 red, and 6 blue. If we pick a shoe at random and then replace it before picking another shoe, draw a tree diagram for this situation and fill in all the probabilities. Okay, so again, sometimes it's important to plan these. They can take up a bit of space. So we have white, red, and blue shoes. The probability of choosing a white is 4 out of 12, a red 2 out of 12, and the blue 6 out of 12. Again, note the probabilities in this branch all add up to 1. On the next drawing, if you chose a white the first time, you could still choose a white, a blue, a red the second time. If you chose a red the first time, you could still choose a white, a blue, a red the second time. And if you chose a blue the first time, you could also choose a white, a blue, or a red the second time. Now again, filling in the probabilities, if you chose a white the first time, and then you choose a white again, the probability of choosing a white the second time, there would be one fewer white in the bag, all right, and one fewer in total. So that would give a probability of 3/11. If you chose white the first time, both reds are all 6 blues are still in the bag, so that probability would be 6/11. Both reds are still in the bag, and that probability would be 2/11. Again, notice how the probabilities add up to 1. Okay. Again, if you chose a red the first time, all 4 whites would still be in the bag. The probability would be 4/11. Again, if you chose a red the first time, all 6 blues would still be in the bag, to give a probability of 6/11. But if you chose a red the first time, there would be 1 fewer red, and so that would give a probability of 1/11 for a second red. And last, if you chose a blue the first time, all 4 whites would still be in the bag, but there would be 1 fewer one fewer shoe overall, 4/11. If you chose a blue the first time, probably choosing a blue the second would result in 1 fewer blue, so 5, and again 1 fewer shoe overall out of 11, 5 out of 11. And again, the probability of choosing a red, both reds would still be in the bag, and that would be 2 out of 11. Again, notice that the probabilities in each branch add up to 1. Now to answer the questions, what is the probability of picking 2 red shoes? Again, you can use some form of notation, probability of 2 reds if you want. So now what you're going to do is you're going to follow the branch that has 2 reds. So that would be this branch here. And you're going to multiply their probabilities. You're using the multiplication rule that we learned on the first slide. So the 2 probabilities multiplied, 2/12 times 1/11, resulting in a probability of 2 out of 121. And then in part C, what is the probability of picking a blue and a white shoe in any order? So really what we want now is we want blue and white in any order. Again, look for every combination of blue and white. So that would be this branch here, that's a white and a blue, and this branch here, which is a white and a blue. So now what we want to do is we want to take each of those pairs of probabilities. So it would look like this, 4/12 times 6/11. And I'll list those outcomes at the side. This is white-blue. This one is blue-white. All right. These blue and white and blue, those are actually mutually exclusive events, so we can simply add those probabilities. So we'll keep the 4/12 and the 6/11 that together, and we'll multiply the other pair of probabilities, which are 6/12 times 4/11. Again, you should notice that those probabilities are the same. That should happen. That's obvious. It doesn't matter the order. Which gives it a total probability of 48/121. Next problem. A hat containing tickets with prime numbers with numbers 1, 2, 3 up to 20 printed on them. If 3 tickets are drawn from the hat without replacement, determine the probability that all are prime numbers. Let's first identify the prime numbers in this problem. The primes are 2, 1 is not prime, 3, 5, 7, 11, 13, 17, and 19. As you can see, there's a total of 8. And the way I'll set the tree diagram up for this problem is the two possibilities when you pick a ticket from the hat is you could either pick a prime or not prime number. These are the only two scenario that we're interested in. And the probability of picking a prime is 8 out of 20. The probability of picking a non-prime then has to be 12 out of 20. And what we're interested in is seeing what the probability of choosing all 3 prime would be. So we could expand the entire tree, but there's only one particular branch I'm interested in, so I'm only going to expand that branch. So again, if I chose a prime the first time, there's 1 fewer prime and 1 fewer ticket in the bag. So it would result in a probability of 7 over 19 for the second prime. And again, for the third draw, again, I'm only interested in the case of drawing another prime, which again, from the previous draw, there was already only 7 primes left. And if one of those primes had been chosen, that would result in a probability of 6 over 18 for the third prime. So now, to calculate the probability of 3 primes, you simply multiply along the branch with the tree diagram. This is your general rule for your tree diagrams. You're allowed to multiply along the branches, and you can combine outcomes at the end by adding. So this would be 8 over 20 times 7 over 19 times 6 over 18, which would give a probability of 336 over 6840. And just make sure you can do that now. You can convert that to a decimal if you need to. All right, and then one more problem. Julie is deciding whether to visit Andrew, Martha, or George. The probability that she will visit Andrew is 0.7. The probability that she will visit Martha is 0.2. And she'll take her friend either to the cinema or to eat in a cafe. If Julie visits Andrew, the probability that she will go to the cinema is 0.6, but if she visits Martha, it is 0.3. If she visits George, it's equally likely they will go to a cinema or cafe. So we'll set up the tree diagram again first. First of all, the 3 different events that could happen are the 3 friends that she might visit, which are Andrew, Martha, or George. And again, those probabilities for visiting Andrew is 0.7. Probability of visiting Martha is 0.2. And again, using the rule that the probabilities in the branch of a tree have to add up to 1, that means that the probability of visiting George must be 0.1. All right. And now, if she visits Andrew, they may go eat or they may go to the cinema. If she visits Martha, they may go eat or they may go to the cinema. And if she visits George, they may go eat or they might go to the cinema. For Andrew, the probability of going to the cinema is 0.6. And therefore the probability of going to eat is 0.6. Let me change that. So the probability of going to the cinema is 0.6. The probability of going to eat then is 0.4. For Martha, the probability of going to the cinema is 0.3. The probability of eating then is 0.7. And for George, if both are equally likely, that means they're both 0.5. So now we have our tree filled out. Now we should be able to answer the questions. Find the probability that Julie will visit George and go to the cinema. So for B, part 1, we're looking for the probability of George and cinema. So we simply multiply along that branch. That is George and cinema, which is this branch right here. Multiply the probabilities. It's 0.1 times 0.5 for an answer of 0.05. In part 2, we're looking for the probability of eating. So now we want all the branches that end in eating. So we want Andrew and eating, Martha and eating, and George and eating. And like I said, we'll multiply along the branches to get those probabilities, but then we'll add those to combine them. And so again, we'll follow those branches. Like so. So what this will result in is the product of those probabilities. So for Andrew, 0.7 times 0.4, plus for Martha, 0.2 times 0.7, plus for George, 0.1 times 0.5. Multiply the probabilities, 0.28 plus 0.14 plus 0.05 for a total probability of 0.47. And then last, the question is the probability of eating. And now here's a more subtle way of asking a conditional probability question. Eat in a cafe if she does not visit Andrew. And by saying if she does not visit Andrew, that's like saying given, not Andrew. So again, using our formula, the probability of eating and not visiting Andrew over the probability of not visiting Andrew. So eating and not visiting Andrew is equal to 0.19. And the probability of not visiting Andrew is 0.3. Should express this as a fraction, multiply by 100, so we get 19 out of 30. And that answers that question. Now go ahead and try some of these homework questions on your own.